Hi Chem 110H, Dr. Bevilacqua here to go over the flipped portion of the lecture on real gases. I want to begin where I left off in lecture, and that was going over the specific condition of 1 mole of nitrogen at a low temperature and a high pressure. And we asked the question whether or not PV equals nRT. And moreover, we asked, once we got our answers, the sample dominated by attractions, repulsions, or is it ideal? And in order to evaluate this, we calculate Z, which is equal to PV over nRT. And if PV equals nRT, then Z will be 1. And if Z is less than 1, the sample will be dominated by attractions. If it's greater than 1, by repulsions. And again, if it's equal to 1, ideal. So we go ahead, we plug in the value for P, V, N, R, and T, cancel units. I've done it here in a color-coded way. And we come up with the answer that Z is equal to 0.595, or approximately 0.6. We can see that this sample is clearly dominated, in this case, by attractions. We also showed in class that another way to understand and work with Z, also known as the compressibility factor, is to think of it as the real molar volume divided by the ideal molar volume. And I thought this was a good opportunity to show you guys that. And so the real molar volume is the volume that's given in the problem. Back on the previous page, we saw that the molar volume was 0.109 liters, and it was in 1 mole, or 0.109 liters per mole. So then we can go ahead and calculate the ideal molar volume, and we can compare the two. The ideal molar volume, V over N, comes from the ideal gas equation, because it's what the molar volume would be if the gas were behaving ideally. And we can easily show that V over N is equal to RT over P. We can then go ahead and plug in the values that were given for RT over P, and we can see that were the gas behaving ideally, its volume would be 0.183 liters per mole. That value is considerably bigger than the real molar volume, which is only 0.109. We can then go ahead and ratio those two numbers, and we get the same Z that we got on the previous page, 0.595 in its unitless, just as we expect we would. So let's continue on. I've copied over here onto the next page that Z is approximately 0.6, and that this is comes about from the real volume over the ideal volume. And like we often do, it's nice to generate a picture to see what's going on and to try to understand it. So I've put it in here into the vessel representative 10 different copies of the molecule, which in this case is equal to nitrogen. And then we've put it under these conditions that lead to non-ideality, really low temperature and high pressure. High pressure forces the molecules close together. At low temperature provides little kinetic energy to overcome those attractions. We can then go ahead and take the real system, and we know that the system is acting with a molar volume of 0.6, or in other words, the 10 particles are really acting like 6. And because there's still 10 in here, the other 4 will go ahead and form dimers out of them. And so this is a good way to think about it. We think stickiness, we think 10 particles have become 6. In order for that to happen, 4 of them became dimers. So on this page, I've gone ahead and sketched out a set of axes for a compressibility curve. Let me just walk through this with you for a moment and explain the features of it. The y-axis is Z, the compressibility factor, equal to PV over nRT, and the x-axis is the pressure at all pressures, extending from moderately high to very high pressures. When the system is behaving ideally, PV equals nRT, and so Z is equal to 1. And that would be true at all pressures if the system were behaving like an ideal gas. It's customary to show that with a dashed line that extends horizontally across the curve. If the system is dominated by attractions like we saw in the preceding example, then the value of Z will be less than 1 because the molar volume is less than, the real molar volume is less than the ideal molar volume due to the attractions. If, on the other hand, the system is dominated by repulsions, then the value of Z will be greater than 1, and we'll look at this in more detail in the coming week. We can then go ahead and plot our point from the preceding example. When the pressure was 100 atmosphere, the value of Z was equal to 0.6. If we were to do a lot of those experiments and place those points on these axes, we would end up with a curve like this, and we can see that at moderately high values of P, Z is dominated by attractions, and at very high values of P, Z is dominated by repulsions. Do some really useful things with them. So this is a CO2 fire extinguisher. This is definitely not behaving as an ideal gas. It's under really high pressure. And you played with these a little bit before. Okay. To wake you up. So they use these to put out a fire. But you want to feel the nozzle. How's it feel? It's really cold. I won't squeeze it, I promise. Okay. It's really cold. You guys want to cool off? Can you feel that?
Yeah.
It's kind of cold.
Have a couple little springs.
Okay. So we'll talk about. So here I'd like to walk you through the CO2 fire extinguisher demo that we did briefly at the end of the last class. This is to illustrate the Joule-Thomson effect. And we began with a CO2 fire extinguisher. It's under very high pressure, approximately 50 atmospheres, which can be read off of the meter on the fire extinguisher. And then we went ahead and fired it, and what happened is that the CO2 that was inside of the cylinder came out into the room. Because it's under such high pressure, it actually is dominated by attractions and forms dimers and probably trimers and other species. As these expand out into the room, they start to become monomers. Why does that happen? Well, they have a certain amount of kinetic energy, and that causes them to kind of wiggle free of their partner and turn into monomers. The room into which the carbon dioxide exits is approximately a vacuum compared to what was inside the cylinder. And because of that, the pressure, the external pressure, is close to zero, so in a relative sense, the work is approximately zero. And because the room is approximately a vacuum is empty space and there's nothing to exchange heat with, so Q is approximately zero. If that's true, then delta E, which is the sum of Q and W, itself must be equal to zero. Given that, delta E, which is also equal to the sum of delta KE and delta PE, is zero. And so we know that delta KE must equal minus delta PE. So what's the change in potential energy? Well, because we're breaking bonds as the dimers go and form monomers, we know that the potential energy is increasing and that delta H is positive, but we also know that the system's becoming more disordered. We're creating more particles, and so delta S, the entropy, is positive. So this endothermic reaction is driven by an increase in entropy. We can then look at the delta KE in more detail. Because delta KE in this particular case is equal to minus delta PE, because delta PE increases and is positive, therefore delta KE is negative. And because delta KE is equal to 3/2 R delta T, as the system becomes an ideal gas, something we derived in class, then we know that delta T itself must be negative. And this can explain to us why the system gets cold. In other words, as the gas expands, it spontaneously goes from dimers to monomers because of the increase in entropy. That increase in potential energy comes from the molecules sacrificing their own kinetic energy, and they get cold. Essentially, no heat or work is transferred in this process. We can draw the Venn diagram for this, and because no heat or work are involved, or in particular because no heat transfer is involved, this is called an adiabatic system or an adiabatic expansion. And the external surroundings, because they don't allow heat transfer, are insulated. If we allow the exchange of heat into the surroundings, then eventually the dimers going to monomers, which is an increase in potential energy, this kinetic energy will eventually return to zero. In order for that potential energy to have increased, heat flows in this particular case, and then the surroundings get cold because of their loss of heat. And this is essentially how your refrigerator works, and it's also the reason why the nozzle on the CO2 fire extinguisher became very cold. Lastly, I'd like to illustrate how these principles apply to the Big Bang, which is won the Nobel Prize for explaining the origin of the universe, and that began about 14 billion years ago. The temperature of the universe during the Big Bang is thought to be about 3,000 degrees Celsius, extremely hot, and the temperature of the universe now is only 2.7 Kelvin, actually quite cold, approaching absolute zero. Why is this? Well, in this particular Venn diagram, it just is the universe, because we're talking about the universe. The change in potential energy is positive, as molecules which are stuck together begin to unstick as their entropy increases. That increase in potential energy comes from the dimer sacrificing its own kinetic energy, and as it loses its kinetic energy, it goes from warm to cold. Thanks for listening.